Welcome to our chapter 7.4 lesson video. Today we're going to talk about something called an infinite geometric series. So this is a specific type of series that applies to geometric series where there are an infinite number of terms, meaning the series goes on forever and ever and ever and ever and ever, ever, and you can add them all up. Now, that may sound a little daunting. Don't worry, we don't have to keep adding numbers over and over and over for infinity. That would be a bit awful, but there is a way to do this for certain geometric series, and that's the big part, is being able to identify which ones it works for and which ones it does not. Let's go ahead and dive on in. All right, so our goal today, I can find the partial sums of an infinite geometric series, and I can find the sum of an infinite geometric series. All right, so let's go ahead and let's talk about what an infinite geometric series is. So we've talked about geometric series before and the pattern they take, and we've talked about how this number down here is the number we're multiplying by over and over and over and over and over. Okay, so that's the number that we multiply by. So an infinite geometric series has an unlimited number of terms and no final term in the sequence, which means that our other geometric series formula, where we have to have Gn, doesn't quite work because there is no n, there is no ending to these series. Now, there are two types of geometric series. The first one is called a convergent series. Convergent meaning it goes to a specific place, a specific number. And when you look at a graph of a convergent series, kind of where you just plot each of the values one after another, you'll see that it kind of plateaus. It kind of reaches what could be seen as like an asymptote where it'll stop. It reaches kind of this maximum value, this maximum location. Now, this is great. If it reaches this maximum location, we can use that for approximation purposes, and we can say, yes, this does converge, which means it does have a sum. The other type is what we would call a divergent series. Divergent meaning it doesn't go to one single location. It gets bigger and bigger and bigger and bigger and bigger forever and ever. So every time you add something new, there's always something bigger and more to add on top of it. You can see this here. It kind of just shoots up to infinity. Now, this convergence and divergence is always based on just one thing. It's based on your common ratio. If your common ratio is the absolute value, so it doesn't matter positive or negative, but if it is less than 1, so if it's a number between -1 and +1, so absolute value less than 1, it does converge, which means you can find the sum. Now, if it doesn't converge, meaning it's divergent, then that means that your R value is going to be bigger than 1 or less than -1. It's going to be making it get bigger and farther away each time something happens. So when I give you an infinite geometric series, the first thing you have to notice is you have to notice the R value. If your R value is the absolute value of it is less than 1, so something like a half, a third, a fourth, 2/3, all those numbers that are between -1 and 1, it works, and you can move on and use this formula we're going to talk about in a second. However, if it doesn't, if it's a number like 2, 3, -7.8, then you would say no sum, diverges. It doesn't go to a fixed point. All right, so let's go ahead and let's test this out a little bit. So we got to determine if the infinite geometric series converges or diverges. All we need to do here is determine what is the R value. So in our first one here, we go from 1 to 5. To get from 1 to 5, we multiply by 5. From 5 to 25, we multiply by 5 again. So here our R equals 5, which means it diverges, which means the infinite series would not have a sum. However, this next one, if we found a couple of these terms, we could do that real quick. So 4 times 1/2 is 2, times a half again is 1, times a half again is 1/2. Our R value here, each time we're multiplying by 1/2. R equals 1/2. Since 1/2 is less than 1, we can go ahead and say this one does converge, which means it would have a sum. So the very first thing you have to do, anytime I give you an infinite geometric series, you have to determine whether it diverges, is it getting bigger infinitely and multiplying by something bigger than 1, or does it converge, meaning that it multiplies by something smaller than 1 and it kind of starts to focus in on a single point. All right, so here is our formula. For a sum of a geometric series, the following formula can be used when the geometric series has an r less than 1. So if it converges, if it has that r value less than 1, then we can use this formula right here in order to find the sum. All you have to do is formula, it's actually a pretty straightforward formula, is you say the first term is on top, and then you do 1 minus your common ratio on bottom. Pretty straightforward formula. This gives you the sum of the series. And notice we don't say S sub anything because we're not adding up a certain number of terms. We're adding up an infinite number of terms, so it's just S. And this is the sum of the series. All right, so nice, pretty straightforward formula. I'd add this to your list of formulas. If you didn't do that already, I'd go back, make sure you have all those formulas written down on an index card, nice, easy to reference, close by, something you can look at often. It'll be real helpful to you. All right, so let's go ahead and try this with a couple of these problems, okay? So first thing we're gonna do is we're gonna look for our R value. On this first one, we go from 11 to 11 over 5 to 11 over 25. Now, if you don't see it right away, you can use the formula. You could go, all right, I have 11 over 5 divided by 11. 11 over 5 divided by 11, multiplied by the reciprocal, you get 1 over 5 for your R value. 1/5 is less than 1, so that's good. Our first term here is 11, and hey, we have enough information to use our formula. So we'll say the sum of the series equals our first term 11 over 1 minus 1/5. Oops, I wrote 1/2. I meant to write 1/5. Let's fix that. All right, and then this is where our skills with complex fractions that we learned about earlier is going to come in handy. We're going to multiply everything by 5 to get rid of that fraction on bottom. Okay, that will give us 55 over 5 minus 1. So that is 55 over 4 is the sum of this series. That was it. Not too hard. Let's go ahead and try the next one. So the next one, right off the bat, we can look at the equation and this number that's being raised to the end. That's our R value. So we can go ahead and just, bam, right away, we could say our R equals 2 over 3. And then we got to find the first term. So we'll plug in 1 for n. So we'll say 3 times 2 over 3 to the first. The 3's cancel. That leaves us with a 2. All right, so that is our first term, A1. Just do the formula like I did last time. Take care of the complex fraction. So we're going to get S equals, our first term is 2 over 1 minus 2/3. All right, this time I'm going to multiply everything by 3 to get rid of that denominator on the bottom. I guess I didn't cross it off up here. I'll do it down there. Bam, bam. So I get 2 times 3 is 6 over 3 times 1 is 3 minus 2. So that's 6 over 1, which is 6. All right, and then our last one, same idea. All right, our R139, if you need to calculate it using the formula, you can. You can go 3 over 1, which is 3. And then you could say, all right, my first term, you just look at the picture, it's 1. And so at this point, hopefully we notice we have an issue. Our R value here is 3. It has to be less than 1. 3 is not less than 1. So we don't do any calculations. We just write no sum or divergent. And you are done with the problem. All right, with that, you should have enough information to be able to get started on the assignment. If you have any questions, please reach out to me. Otherwise, I'll see you in our next live session. And until then, I hope you have a great day.